All right, good afternoon. Welcome to Wednesday, week 3. So today I want to talk about like terms. We're going to do an introduction to like terms. We're going to talk about how we deal with like terms, adding, subtracting, and multiplying, and how we're going to use them when dealing with 1, 2, and multi-step equations. So I want to start a conversation with like terms with shoes. So let's talk about shoes. So I have not very many pairs of shoes. I have 2 pairs of shoes. So I'm going to indicate pairs of shoes just with this little symbol. I'm going to say I have 2 pairs of shoes. And then for my birthday, I got another pair of shoes. So I'm not going to write the 1 because I think just one image is enough. So I have 2 pairs of shoes and then I add a pair of shoes. Well, how many pairs of shoes do I have? I have 3 pairs of shoes in total. So let's say now I have 3 pairs of shoes. And over the winter, I've worn out 2 pairs of shoes pretty bad. They're caked with salt, so I threw them out. So I've lost 2 pairs of shoes. How many pairs of shoes do I have now? Well, I have 1 pair of shoes. I'm not going to write the 1, so I'm just going to say 1 pair of shoes. And drawing shoes kind of sucks, so I'm not going to draw a shoe. Let's just say that I'm going to let a shoe be represented by X. So now I have X shoes. I have 1 shoe, so I'm going to represent that by X, and I go out and I buy 3 pairs of shoes. I represent that with 3X. So I had 1 pair of shoes to start with. I've added 3 pairs of shoes. How many pairs of shoes do I have? I have 4 pairs of shoes, or 4X. So we use variables to represent things that we just don't know what the number of that thing is yet. So when I'm adding variables, so when I'm adding like terms, and we'll discuss what a like term is shortly, but when I'm adding like terms, I'm really just adding the coefficient in front of the variable. And a coefficient is the number that we find in front of the variable, or in other words, the number that's being multiplied by the variable. So here I have 3 shoes minus 2 shoes up here. So I have 2 is the coefficient here, or rather negative 2 is the coefficient here, 3 is the coefficient here, and I'm taking 3 shoes, subtracting 2 shoes, and I get 1 shoe, although we don't always write the 1 in front, so it's just a single shoe. All right, let's stop talking about shoes, and let's go back to variables. So when I'm adding variables, I just add or subtract the coefficients in front of the variable itself. So let's say I have 4y minus 2y. Well, here I have 4 y's in total on the left side. On the right side, I have 2 y's. So 4 y's here. I'm taking 2 y's away. What do I have left? I'm left with 2 y's. It works with any variable. If I have 10 m's and I'm adding another 3 m's, how many m's do I have in total? Well, I have 13 m's. Now, this only works if we're dealing with like terms. So that begs the question, what is a like term? A like term, a term, first of all, is separated by addition and subtraction. So if I have an expression, and my expression is 3m plus 4x minus y plus 2. This expression has 4 terms. A term is separated by either addition or subtraction. So it's a set of constants and variables that are either being multiplied or divided together that are separated by addition or subtraction. So every time I see an addition or a subtraction symbol, I'm separating terms. So this is term 1, this is term 2, this is term 3, and this is term 4. These 4 terms are all unlike each other. None of them are like terms. In order for something to be a like term, it has to share the exact same variable with the exact same exponent. So let's go down one. Here's a bunch of different terms listed on the page. I want to find the terms that are alike. And in order to find the terms that are alike, I need to make sure that that term has the exact same variable. The coefficient, in other words, the value in front of the variable, can be different, but the variable itself must be exactly the same. The exact same variables with the exact same exponents. So let's start with this 3y right here. I need to find another term that is like 3y. So another term that has possibly a different coefficient, but the variable is exactly the same. The only variable that that term can have is a y. So let's look around. I see that 7xy has a y, but it also has an x, which means its variables are not the same as 3y. 3y and 7xy are not like terms because it's got this extra x that the 3 doesn't have. Okay, well, let's look over here. Negative 7y squared. So this has a y, which is great, but it also has this exponent of 2. The 3y does have an exponent, even though we don't write it in. The exponent is always assumed to be 1. Well, the exponents don't match between 3y and negative 7y squared because this exponent ruins it for us. So they're also not like terms. Looking down over here, we have negative 19y. That's a potential. So the coefficients are different, which is fine. We still have a y, and the exponent on the y is exactly the same. They're both 1s. So these actually are like terms. Let's try something different. Let's work with 7xy. So I'm looking for a term that may have a different coefficient, but has the exact same variables behind it. Well, we have 2xy, and we have this 3x squared y, which might seem like it's a like term. However, the powers on the 2xy are both 1, so this is an x to the power of 1, y to the power of 1. This x to the power of 2 completely messes it up, and so those are not like terms. There actually isn't another set of like terms for 2xy. Those are the only two on the page. Let's try negative 8m times n. Let's see, do I have another negative 8? So it doesn't matter if the coefficient is different. Well, we have a negative nm, and so this is a negative 1, even though it's not written. So mn, so it has an m, it has an n. However, they're in the wrong order, but that's okay because we can multiply in any order we want. And when we write out a term like this, the operation between the n and the m is really just multiplication. And because we can multiply in any order, m times n is the same as n times m. These two are actually like terms. They both have an n to the power of 1, they both have an m to the power of 1. It doesn't matter what order they're in, it still counts. Okay, let's see what else I have. I have an 8p. We have a negative 1p here. And I think those are the only two. I think all the others are unlike terms, so they're all just individual terms. All right. So let's try our first expression where we have to collect like terms. And the word collect like terms, collect just means to add or subtract all the like terms. So collect like terms, you might also see simplify. These just mean add or subtract like terms. So let's look up here. I have 3x minus 4m plus x minus m. Well, I can't do 3x and 4m because they're not like terms. So let me actually just underline in blue like terms. So 3x and positive x, those are like terms. And then negative 4m and negative m are like terms. So I'm going to start off with the terms with x. So I'm going to take 3x and I'm going to add it to positive 1x. So 3x plus positive 1x. So basically I have 3 x's here, I have 1 x here, 3x plus 1 x, that's 4 x's total. Here I have negative 4 m's, and then I'm taking another m away. So if I had negative 4 m's and I'm taking another m away, that's going to be negative 5 m's. I would love to go even further, but I can't subtract 4x and 5m because they are unlike terms. And if they're not like terms, there's nothing I can do. So the expression stays right there, and my answer is 4x minus 5m. Okay, the other case I want to talk about is an expression where we have to distribute, so use distributive property before we collect like terms. So let's go back up here and let's talk about multiplying or dividing terms by a constant. So let's go back to talking about shoes. So I have 2 shoes, and that's not enough shoes. So I'm going to double the number of shoes that I have. So I'm going to multiply the number of shoes that I have by 2. And instead of writing x, because we don't like to write multiplication symbols like this in algebra because it gets confused with x, we like to use dots instead. So either we'll use dots, so this means 2 times 2 shoes, or what you'll see most commonly is we'll just put brackets around one of the terms. So we'll put brackets around here, and if you see a constant or a term right next to a bracket without anything written in between, we can assume that it's multiplication. So this is just assumed to be multiplication, 2 times 2 shoes. Well, if I have 2 shoes and I multiply the number of shoes by 2, I suddenly have 4 shoes. So I multiplied the constant by the coefficient in front of the variable. So instead of writing shoes, let's say that I have 3 x's. And I'm going to quadruple the number of x's that I have. So I'm going to multiply it by 4. So instead of having 3 x's, I now have 4 times that. So 3, 6, 9, I have 12 x's. We can extend this to the distributive property, which we've learned before. So if I have 3 x's plus 2 y's, and I want to multiply that whole thing by 2, this sort of breaks BEDMAS. I can't really multiply before I add or subtract, because according to BEDMAS, I have to do what's in the brackets first, and then exponents, and then I can do division and multiplication. And this is in the brackets right here. This 3x plus 2y is inside the brackets, but I can't do what's in the brackets because these are not like terms. And because they're not like terms, I'm sort of stuck. I'm sort of stuck right here, and I can't go any further. But we have this method called distributive property where I can sort of bypass BEDMAS. I have a cheat that I can get away with as long as I follow this simple rule. If I take the number that I'm multiplying the bracket by, I can, instead of doing what's in the bracket first, I can distribute this multiplication of 2 or this factor 2 into every single term in the bracket. And there's 2 terms here because a term is separated by addition and subtraction. This is the addition symbol, so 3x is one term and 2y is another term. I'm going to distribute the 2 into both those terms, and what I'm going to get is 2 times 3x's, that's going to give me 6x's. 2 times 2y's, if there's 2 y's and I double it, that's going to give me 4 y's. And that's where I stay. I can't go any further because I cannot add 6x plus 4y because they are not like terms. So let's carry this forward onto our problem down here. I have 9 times what's in the bracket. So 9 times x minus y. Whoops, wrong tool. 9 times x minus y. And then I have plus 3x and minus 2y. And whenever we have a situation like this, we like to do the distribution first. So I'm going to distribute first, and then I'm going to collect like terms. So step 1, distribute. We will also see this written as expand, because it usually makes the expression longer, so it expands the expression. And then step 2, I'm going to simplify, which is another way of saying collect like terms. So starting up here, equals. I'm going to do my distribution first. This is 9 times x minus y. I can't do what's in the brackets because they're not like terms, so I'm going to use my distributive property. 9 times x, 9 times negative y. Well, if there's nothing written in front of the variable, I know that there's a number there. I know that it's 1. So I'm going to put 1 on each side. 9 times 1x. So if I have 1x and I multiply it by 9, I suddenly have 9 of them now. Here I have negative 1 y's. Negative 1 times 9, that's negative 9 y's. And then I'm just going to write plus 3x and minus 2y. And as soon as I distribute the 9 into the brackets, what I'm basically saying is I've done what I should with the brackets, and the brackets disappear. So as soon as you distribute, you can remove the brackets, and so my final expression here after doing the distribution is 9x minus 9y plus 3x minus 2y. So I'm done my distribution. There's nothing else to distribute. There's no other brackets I have to deal with. So I can move on to simplifying and collecting. So I'm going to identify all of my like terms. Well, I have a 9x, negative 9y is not like, but the positive 3x is. And then I have negative 9y and negative 2y. I do like to highlight my like terms. Obviously, if you don't have a highlighter, you can just use either underline and circling. So you can underline the x-like terms, you can circle all the y-like terms, but it is nice to be able to identify all the like terms, especially as expressions get bigger. You sometimes lose track of all the terms. So here now I'm just going to collect all the terms that are alike. This is 9x, this is positive 3x, so I'm going to do 9x plus 3x. And here I'm going to have negative 9y minus 2y. So negative 9y minus 2y. Here I just rearrange them so that the like terms are side by side, so it's easier for me to deal with. And then I have 9x plus 3, so that's going to give me 11 x's. And then I have negative 9y's minus 2y. So if I have negative 9 and I'm subtracting 2, I'll have negative 11y. I can't go any further than that because these are not like terms. And so that's my final expression, and so that's what I write. We're going to end there. Friday, I'll put up a tutorial. We'll talk about 1- and 2-step equations, and that's going to prepare us for next week when we're going to talk about multi-step equations or solving multi-step equations. So enjoy the rest of your day, and remember there'll be tutorials tomorrow at 1 o'clock if you want to come in and get some help. It'll be on Microsoft Meets.